Hey everyone, welcome. Today we're going to tackle a classic physics problem, Irodov 1.101. Now, I know this one can be a real stumbling block, but trust me, stick with me through this explainer, and you'll walk away with a super powerful new technique for your problem-solving toolkit.
So let's just dive right into the heart of the problem. You know those standard kinematic formulas you learn? They're fantastic, but they have one massive limitation. They only work if acceleration is constant. So what on earth do you do when the force, and therefore the acceleration, is changing as you go? Well, that's exactly the puzzle we're facing today.
All right, so here's the actual problem we're up against. We've got a bullet, it goes through a plank, and it slows down. Seems pretty straightforward, right? But that last little bit, assuming the resistance force to be proportional to the square of the velocity, well, that's the part that changes everything. It's our big clue that the acceleration depends on how fast the bullet is going, which means our usual bag of tricks just won't cut it. Okay, every good detective needs to lay out the facts, right? So let's do that. Our knowns, these are our clues, are the plank's thickness, h, and the bullet's starting and ending velocities, v0 and v. The unknown we're trying to figure out, the big mystery, is the time, t. And the one rule that governs this whole thing is that the resistance force is proportional to v squared.
So where do we even start? Well, in mechanics, no matter how tricky things get, your first move is almost always the same. Newton's second law, F equals ma. It's the rock-solid foundation we're going to build our entire solution on.
Okay, so now we've got to translate all that physics into the language of math. The force F is proportional to v squared, so we'll write it as negative kv squared. Now do not, I repeat, do not forget that negative sign. It's absolutely critical. It tells us this is a resistance force, it's always fighting against the direction of motion. And acceleration, a, well, that's just the definition. It's the rate of change of velocity, dv by dt.
And boom, when you put it all together, you get this equation of motion. Now this is what we call a differential equation. But don't let that big name scare you off. All it really means is that it connects a variable, in this case velocity, to how fast it's changing. And to get our answer for time, we're going to have to use a little calculus.
Okay, so what's the standard playbook here? We rearrange the equation. It's a technique called separation of variables to get all the velocity stuff on one side and time on the other. Then we integrate both sides. Time goes from 0 to our final time t, and velocity goes from its initial value v0 down to v. And we get a formula for time. Looks great, right? We're done?
Or are we?
And this right here is the trap. It's where so many people get stuck. Take a good, hard look at our answer. It depends on m, the bullet's mass, and k, that proportionality constant. The problem is, we weren't given either of those. This is such a classic pitfall. You get an answer that's mathematically perfect, but you can't actually calculate it with the info you have. That means our first attempt, while a good start, isn't the whole story.
You know, when you hit a wall like this in physics, it's not a sign you did something wrong. It's usually a clue that you need to come at the problem from a totally different angle. We've already looked at how velocity relates to time. But hey, remember that other variable we were given, the Planck's thickness, h? We haven't used that yet. Let's see if we can connect our physics to position.
And this leads us to a really cool trick. It's kind of like a secret weapon in mechanics. We all know that A equals dv dt. But by using the chain rule from calculus, we can rewrite it as a equals dv dx times dx dt. And what's dx dt? It's just velocity, v. So this gives us this awesome new expression for acceleration. A equals v times dv dx. This is the key because it connects acceleration not just to time, but directly to position.
Okay, armed with our new tool, let's go back to Newton's law and try this again. We're going to substitute our new expression for acceleration right back into F equals ma. The force on the left side is still negative kv squared, but the right side now becomes m times v times dv over dx. We run the same play as before. Separate the variables and integrate. But this time, we're integrating over distance from 0 to h and velocity from v0 to v. We do the math and look at this. We get an expression for h that has that same pesky m over k ratio in it. This is it. This is our aha moment. We've just found a way to define that unknown chunk of variables using only the stuff we know.
So check this out. We now have the two pieces of our puzzle. On one hand, we have our first equation for time, which was stuck because of that unknown m over k. On the other hand, we have a brand new equation that tells us exactly what m over k is using only our known variables. You see where this is going, right? All we have to do is take our new expression for m over k and substitute it right into our time equation. A little bit of algebra later, and there it is, the final answer. The time it takes the bullet to get through the plank, expressed entirely in terms of the variables we were given at the start. Case closed.
So, what's the big takeaway here? It's not just about this one formula, it's about the strategy. So let's add these to your detective toolkit. 1. Always start with the fundamentals, like F equals ma. 2. If you run into unknown constants, don't panic. It's a clue that you need to find another relationship. And 3, remember that A equals v times dv by dx is your secret weapon anytime a problem connects force, velocity, and distance.
This two-pronged attack, where you find two different relationships to solve for an unknown constant, is an incredibly powerful strategy. So I'm going to leave you with this question. Where else could you use it? Think about problems with springs, right, where the force depends on your position. Or maybe even orbital mechanics, where gravity changes with distance. Keep an eye out for these kinds of problems, because now you have the tool to crack them.